Evening, everyone. I really hope everyone is well and healthy. Thank you for introducing me and mentioning some of the research I've done. Before we founded Cadami, I would like to give you a bit of an idea what Cadami is and does. We're a small startup here in Munich. It's privately owned. We're currently a team of about 6 employees. Sometimes we take on some freelance work, and our core product is a implementation of coded caching that can be applied for commercial applications. And this talk, I will give you some ideas on the challenges we faced when we actually implemented coded caching, and we will also I will also show you some aspects on what kind of coded caching we implemented. As I said earlier, I'm one of the co-founders. The other 2 co-founders, Michael and Maximilian, they've also been researchers at the Technical University here in Munich. So we are a university spin-off. We did some very theoretic, academic, mathematical research, and then at some stage decided that we wanted to get more hands-on and actually implement some of those theories. And coded caching was really what spiked our curiosity. And so I'll give you a bit of an overview here. Very important, if you have any questions throughout these talks, there is like these Q&A option, and I should be seeing those. So you feel really encouraged to pose questions along the talk. Brief outline. So I will give a short introduction about coded caching, and along this one, I will already mention some of the challenges. Then I will discuss 2 applications where coded caching is already used, and another one where it will be used. Then I will talk about some design options and challenges we have when we actually deploy those systems. And then there's really a few things about the challenges we faced when implementing this that usually don't appear in the academic papers. And I think that might be interesting for you as researchers to see some of the path it takes to take very theoretic research like the one on coded caching and then building a implementation at some point. So when we introduce coded caching, we usually go one step back and start with index coding. And one of the easiest examples about index coding is to imagine transmission over a lossy broadcast channel. So in this case, we would have a transmitter, a server. We have 2 clients. And then one client, the one to the left, would want to receive the file A, the one to the right, the file B. And then as randomness occurs in the packet loss, we might face a situation where each of them receives the opposite file, but the one actually desired is lost. And then what index coding can do in such a scenario is offer a clever repair mechanism. So we now have like this situation where each client received the packet he's not interested in, and then index coding would tell us that we can create a combination of the 2 files and send that one instead over the broadcast channel. And if that one makes it to both of the receivers, they will be able to decode their packets. That was a drastic simplification. In general, index coding applies to more users, different types of codings, and it's really a hard problem to at some point find the optimal index code. But that really is the way we would like to introduce coded caching. If we look at this situation where this cache at the client becomes helpful, and then this joint encoding of information reduces load on the network, then this leads us to coded caching, where we would actually not have that situation at the clients caused by randomness and packet loss, but by a specific and maybe carefully designed pre-caching mechanism. And that brings us to coded caching, and that's really the very similar scenario. We have a server, a emitter, we have a set of K receivers, and very important to see the benefits of coded caching, we always assume that all these receivers share a bottleneck. And there are several scenarios matching this one. The one we are particularly interested is one where this is a video transmission system. So in that situation, each of the K receivers would run a video player that accesses a video service on the server offering a on-demand library. And well, I think you've all, or most of you might have seen this plot of the Arley-Neeson scheme. The importance in coded caching is then that it can vastly outperform conventional caching. So here the idea about conventional caching is if I can store all of the library on every client, then the data I will have to transmit later when the clients actually request videos will be 0. If there is no storage at the clients, then any request would create a data traffic on the network. And then here the idea is if I am able to cache 20% of every file, then the load reduces by 20%, 40, and so on. And coded caching being a very optimal trade-off in between the cache size and the data volume. And then you have this very famous formula here that connects the number of users, the videos in the library, and the cache size available. And that Mara-Arley-Neeson scheme, we sometimes call it like decentralized. And what we mean by centralized is the very planned scheme. And the idea in this Mara-Arley-Neeson scheme is really to create all subgroups of the clients. And this will give us a distinct pattern on how we have to segment the files in the library, and then which client will store segments. And then very importantly, it kind of has this, and I will get back to this later frequently, it has this parameter baked in, which is kind of the gain, which is sort of hard configured. So in the earlier scenario, when we looked at the index coding, here we would have combined 2 users. The same applies when we do index coding and coded caching. And there is like in this Mara-Arley-Neeson scheme, there is like this baked in gain parameter, which is how many users you would usually combine in a single transmission. That's like one group of coded caching schemes, and that's actually the one where we have the implementation that we are actually use in live deployments. Also very interesting is what we call like a decentralized scheme. It's much less systematic. Basically, we just split files into segments, and then clients will cache randomly parts of those segments, and then there will be an online mechanism to find the index codes. And both have unique challenges with implementation, and I would briefly want to highlight some of those. So that's the Arley-Neeson scheme. Here in the example, we fixed those parameters. We have 4 users. Every client will have half of the library stored. So in this case, we have 4 titles in the library. blue, yellow, red, and gray. And each of the 4 clients has enough storage to store the equivalent of 2 titles. And then like this baked in number T is the gain in that sense that we would usually jointly encode 3 users. And what is very typical for this Ali-Neeson scheme is files are segmented into something we like to call chunks. Don't confuse those with chunks in like MPEG-Dash or similar things. It's just really on the byte level. So if you assume this would be 600 megabyte, then one chunk would be 100 megabyte. And then in this scheme, we typically see these unique patterns in the cache that every client has. So this one would have the first 3 chunks, and every client would have a unique but different pattern. And this allows us then in a transmission phase to combine user requests. So here the first user would request the red video file, and then the missing parts are chunk 4, 5, and 6. And then for every transmission we need to make to serve all 4 requests, we can always combine 3 of those chunks into a single broadcast transmission. So in this example, instead of delivering 12 chunks, which is 3 missing chunks at each of the 4 clients, we instead only have 4 broadcast transmissions. And that really reduces the load on that network. There's a few things to notice. Whenever we change this parameterization, so any of those parameterizations, the number of chunks we need to create and those patterns change. So it's very difficult in a real-life deployment to actually update those parameters. And you can imagine that's especially challenging if you have scenarios where users randomly join or leave a service. Simply assume maybe a cellular network where people move into a cell or turn off their phones and off, or the service on and off. So, but the real advantage is that everything is like nicely organized, and we kind of already know which users to combine in a transmission in advance. So we can create a highly effective mechanism to find those user combinations. Summarization of these advantages of that scheme is, well, the cache state at the users, the number of users, they are deterministic. So we very much know in advance the behavior of the system. It's deterministic which users are jointly encoded. So we can, like, if we want to, like hard code into that system. And then also that's really an implementation aspect. As we know the maximum numbers of users that are combined, we know how much we have to read off a disk if we want to encode or decode this transmission. So if that number of packets I encode jointly per transmission is more or less a constant, I know what discrete operations my hardware needs to support. I already mentioned the drawbacks. It's very difficult to adapt the user numbers or the gain factors. It's very difficult to add or remove users from the systems. And then also the number of segments that we need to partition a file into grows exponentially. And I think that's a well-known problem. I'll get back to this. The other approach is to say, like, well, instead of having this very structured and pre-planned approach, let's just chunk up files into small segments, have every client more or less storing a portion of those randomly. And then when requests are happening, let's collect all those requests, all those cache states, and make like a big optimization problem on how to optimally solve those requests. And that is nice because contrary to the earlier scheme, computing the cache state at the clients is rather simple. It can, for example, be random. But then it's much more challenging in the request phase. And there's a lot of research out on how to formulate this as graph problems, graph coloring problems, and it's computationally hard. The real advantage is these chunks don't have to get that small. And also a lot of research has shown that these greedy strategy, they might not guarantee the full gain, but usually we're getting good results. Yeah, again, in the comparison, sorry, that's the example here. I used the same cache states. Also in the implementation, we could have the same, and then in the request phase, you would get kind of this graph coloring. Here it's partitioned into two colors, and then for every transmission, I believe you would select two users with different colors. Well, the real advantage here is that design is much more flexible. It's easy to add and delete users. Also, if we would want to upgrade to say like, well, every user should now cache twice as much, that's really easy to achieve. So it's like the flip side of the coin. The caching strategy is now very easy and flexible. The drawback is in the request phase, finding the optimal transmission strategy is difficult. And those online algorithms, they might need a lot of computational power, storage, all these things. And also the opposite to the earlier one, the number of users we are combining is now not static anymore. So it's also a random variable. And we might end up that most of the time we like encode 2 users, but then suddenly we have to encode 10 users. And for that encoding of 10 users, we would actually have to read those 10 packets of disk. So that's just to compare those two and those options, and also to highlight some aspects that they pose on implementation and using in actual applications. I'm going to do like a 30-second break here to give you a chance to type any questions if you have them on this comparison. Otherwise, my next topic is about where we really use codec caching. And the first application I would like to highlight is a in-flight entertainment system. So that's really those systems where each passenger has a screen in his front seat. These screens are typically like small computers, very similar to like an iPad hardware. They got video screens, they got various kinds of operating systems running there. Some are Android, some are Linux. The interesting thing is you have a very high density of people watching video. There is some ideas to do that wirelessly. So in that case, if you put a Wi-Fi access point in that airplane, a lot of pressure on the capacity of that network. But the same applies to wired systems. So aircraft typically get certified for 20, 30 years. So maybe there's a very modern in-flight entertainment system that has nice 4K displays, but then there's like a single 1 gigabit Ethernet. So we really have the situation where network capacity is an issue. We also have the situation that these screens have some storage capacity. Very often that's SD cards. But this storage capacity is not sufficient to store the complete video library offered. To give you some indication, modern aircraft, they have several terabytes of content. Typical storage at the screens might be half to 1 terabyte. So we want to also be very efficient with that storage. And that's really kind of the perfect application for that centralized coded caching scheme. So we can, the number of users will not change. The network configuration is static. There is really opportunity to fill the storage. That's whenever the aircraft is grounded and there is no passengers watching movies. So we can use those times to deploy and fill the caches. And then later, when the aircraft is in flight, all passengers can consume videos. And that's really where our commercial coded caching implementation is used. It's deployed in about 300 commercial aircraft. An idea on the user numbers, there's typically 200 to 450 seats on an aircraft. Another application where we're currently not live yet with our software, but we're doing a significant amount of testing in labs is content distribution networks. So that's really what is used by video services that you're watching over your internet connections. And well, typically there is something called an origin server. Usually that's one per country or one per area. And then not so sure about India. I can give you an example about a country like Germany. There's usually like one origin server, and then every major city would have a regional server. So there's maybe like 30 to 100 of those regional servers. And the idea is really to get content replicated on those regional servers and also make them closer available to users. So the idea here really is to apply coded caching to do two things. We might want to scale the traffic coming into those regional servers, which would usually then create more load to the origin servers for those files that are not stored locally. So coded caching can help us to reduce that load. That's one application we're exploring. That's for existing content distribution networks. The other path we are exploring is would the availability of a coded caching system allow us to consider different deployments? And the idea is really to say, well, maybe let's not have 30 delivery sites, let's maybe have 1,000 or maybe even 10,000. And let's build those with significantly cheaper hardware. So much less storage, smaller and cheaper computers. And coded caching can be an enabler here. So very different story if we look for a match with coded caching. So the user population, that's people on the internet, so they will be variable. Those delivery sites, they might be updated with dynamic provisioning. So it's much more flexible. Still, we're currently considering using the centralized system, just assuming we can afford an update of the caches if needed. And then really, I would like, as a next point, highlight some considerations one needs to take when actually designing such a system. So the one is, if we look back to this trade-off curve in between the cache size and the network load we are seeing in a coded caching system, we still haven't answered which particular point we would like to operate the system in. So we know, well, if we only have a little bit of storage available, we can massively reduce the traffic on the network. But then there's still the questions, is it like this point we're going to operate the system in, or is it maybe this point here? And we obviously have some technically side constraints. For example, we might not be able to choose the cache size at the client. It might just be a given constant. Same might apply to the network. So that might limit the range of operation points we can use. And then if we actually discuss this in the context of a service being deployed, really what needs to come into this model is costs. So, and that costs can be very different. For example, in the Inflight entertainment system, if at the seats there is SD cards, then you kind of can look up at Amazon what an SD card costs. So extending the cache might be an option. Extending network capacity is usually cost prohibitive. It would mean to ground the aircraft, wire new cables, get a new license for the aircraft. Differently in content distribution networks, where you might be able to upgrade your data connection by just renting more. So, but yeah, I think that's really important to highlight that picking this trade-off curve, a point on this trade-off curve, not only is a technical decision, but usually we need to apply some cost metrics. Yeah, I mentioned some of these in the in-flight entertainment system. The network cabling on an aircraft, it cannot really be changed. Also, the request popularities on which content is selected, that's very hard to estimate. So these aircraft, they typically have a home base, but from there they fly anywhere in the world, and people will watch very different videos if they go to the US than if they maybe go to China. So you would have a very hard time guessing which are the popular movies in your offering. Also, there's something to consider if you look at the network load, then we are really not interested in the average load, because that network on the aircraft, it's there, it's been paid for. There is no additional cost for using it. There is, however, a cost if you overload that network. So let's assume you build a system where you maybe store the most popular content at every seat, then the aircraft goes to some exotic area where people have a different taste. They all select unpopular videos. You overload the network, the video system breaks down, and you have an aircraft full of very unhappy customers. So when you make that design choice, you really design for the worst case, and the worst case being every passenger requesting a very unpopular movie. And if we look back to that centralized and decentralized caching, the centralized caching really is an excellent fit here. So it has these carefully designed parameters, and it really guarantees us a maximal network load. And that's really what we're designing for here. So we have these constraints of the network capacity of the cabling that exists on the aircraft. There might be options to upgrade the storage at the clients, and then we really pick an operating point where we stay within the worst case capacity on the network and use as little storage as possible to keep the costs low here. And really that centralized caching is an excellent fit here. Also remember, these aircraft seats stay on board. Although the requests and the popularity changes with the passengers, the cache of that centralized scheme guaranteeing us that worst case network load, they remain and they are static. So again, this is like a perfect fit. Different picture if we look at the content distribution networks. Here, network capacity that we can use for the video service is typically flexible. So it's shared with other services. So it's not only the peak load that matters, it's also the average load we're creating on that network. So the average load is also relevant. Also costs for that network might not only be like provisioning the network once, there might be costs per gigabyte transmitted. On the other hand, we can very well estimate popularities. So typically, like for a TV series, if there's a new episode released, we know this is going to be very popular. So we might want to cache that on the edges. So centralized caching is not flexible enough as we would want it to be. So we're exploring other avenues here.
A quick question.
Sure.
Yeah. So for this content distribution networks, so as you said, right, so there could be an update in the content every week or something like that. It's in that case you would need to do cache updates as frequently as it would be necessary, right?
Yes, you're very right. I mentioned earlier that in the aircraft scenario, we have those dedicated times where we can make the updates. We don't have those in the content distribution networks. We would, however, assume that there is times of low utilization in networks, like overnight time, where we could make those updates. Also, those content distributions would allow us to use coded caching in several hierarchies. So as long as coded caching server and clients are on hardware that is completely managed by the operators, that should be fine. If we extend that closer to the user, for example, including set-top boxes, home routers, smart TVs, or maybe even personal devices, that cache update becomes way more challenging. Those devices might be on and off, they might be connected to a network or not. So very contrary, so that also means it's no longer a good fit with that centralized caching scheme that very much relies on caching being structured and filled as planned. So we feel that as we're progressing to those content distribution networks, that centralized caching is too limited. So we haven't done that yet. We're still testing the centralized caching, but we can already foresee that that we need more flexibility here. Definitely.
Right.
Also, to give you an idea, it certainly matters on how much benefit we have by coded caching, on how often that content changes. Again, to give you an idea, on an aircraft, that's only about once a month. So there is new content coming in once a month. We then update the caches on all the clients, and we're usually able to do this within 2 flights. And then there's like a whole month where coded caching benefits of those caches not changing. And that will be very different in a video service running on the internet, where there's like releases of new episodes every day, and that needs to be very, very flexible. So ideally, we would also have a system here where users with kind of outdated caches or partially outdated caches can still fully participate and then maybe not get the full coded caching gain, but some of it. But yeah, we don't really have a good solution yet in terms of it also showing good performance in the labs. Still not only an open academic problem, but also a problem in what we can build. I mentioned now several times that the popularity of requests, and I think that's also something to keep in mind if we design coded caching systems. So we typically look at this curve that we find in the research paper, where we have this massive gain to a conventional caching, where there's some files or some parts of the files stored. But this curve here usually assumes that requests to all titles in the library have the same likelihood, and that's not true in reality. In reality, we have those things where some of the content is much more popular than the rest, and then this curve looks very different. So that's like one where we do conventional caching, popularity caching, in the sense, if we say, well, the storage size is 25 titles, then this yellow curve here would store the 25 most popular titles, assuming you could predict that. And you see that already gives you a reduction, a massive reduction. So that's really something then coded caching has to compete with. So you can see that the gain by coded caching, if those popularities are in there, might become much smaller than what we typically or what is often assumed in the academic research paper. I think there is efforts out there to include those popularities. We haven't implemented any of those academic results yet. Here's something we do with the centralized caching method, and actually a sort of like really hands-on, really simple idea, but it's something that works with what we already have. So we simply say, well, there is these 200 titles in the library, and then we make a split. In that case, what we did, so this is the request popularity, like if you want, so a cumulative density function. And for example, already the first title in that library will see 17% of the requests. So even if we kind of do coded caching, if there's a title that we know is that popular, we would completely store it at the client. Actually, like storing it at the client would like correspond to a coded caching gain of infinity. So, and then we would say like, well, there is like another 49 titles that are kind of popular. And for those, we would pick a different coded caching parameter. In this case, the coded caching gain of 3, where typically 3 clients are jointly encoded. The point is, if we select that for a title, it will consume more storage than if we pick a coded caching gain of 2. And then coded caching gain of 1 is like the special case where we don't use any storage, but just download the file. And that kind of, that's a very simple method to like bake in the request popularities and say like, well, if a file is more popular, we afford some more storage to get a better reduction in load on the network than for titles that are less popular. So that's what I show here in this plot, is really this operating point here, where we afford a total storage of 5 titles. So we would kind of say like, well, this is a scenario where we constrained in the storage size, and not optimally, but we want to have a scheme that exploits that some titles are more popular than others. And the reason why we did this is because we can just reuse the implementation we already have in kind of just running, if you want, so 2 or 3 or 5 instances of those. But that's really if you do academic work on it. Unfortunately, I didn't follow the very recent results. I know there are some results on how popularity can be considered, but I think that's in terms of practical implementation, that these results would be very welcome, because we know for a fact that in the real world, not all the titles have the same popularity. Do we have any questions on those design challenges and ideas? Okay. Well, then I'm coming to the last chapter of this talk, where I would really want to highlight to you some of the challenges when you actually take the theory and build it. So the first one is this sub-packetization problem. It's those of you that are working on codec caching already know it's a huge thing in academia. I think that list is already very outdated. We know that for these centralized schemes, the number of segments we would have to chunk a file into grows exponentially. And then, well, like the theoretic limit is if those chunks become smaller than a bit, we have a problem. In implementation, those problems start much, much earlier. And that's something I would want to make you aware of. It's not only those chunks becoming very small and very hard to handle. Really, the first bottleneck you will observe when you split a file into very small sizes is that you are creating a bottleneck in how you can read data of your disks. So a typical storage in our computers is highly optimized for linear read. That means reading a file from start to the end. And if we briefly go back to how these coded caching systems are structured, you will see that creating those combinations means at the server, we're not reading a file from beginning to the end. So we're picking some part here, some part here, some part here. And that really creates a problem when reading that of the disks. Disks will fill internal caches with data you actually don't need. And then if you go to small sizes, and to give you an idea, small size is maybe less than 100,000 bytes, you already observe a massive degradation in read speed of those disks. And that really limits on if you look at this centralized scheme, what you are able to deploy on a practical system. And that typically reduces us to a codec caching system where our maximal gain is somewhere 3, 4, 5, or 6. So that's really from all the practical implementation. Well, there's all kinds of bottlenecks you will hit, but that's usually the first one you will hit when you try to squeeze out more performance from codec caching when using schemes that really need to create those small chunks or sub packets. So that's really something you need to or should be aware of if you're ever considering implementing a codec caching scheme. Also, a very interesting and challenge we faced when implementing and deploying those systems is codec caching, and I think that really applies to all schemes, always assumes there is a multicast or broadcast channel. Now assume you build a codec caching system that reduces the network load by a factor of 3, then that's typical the server emit rate. Still, if you, for example, look at a Wi-Fi network, where you would really have to compare yourself to a unicast download system, you also have to take into account if the rate you can achieve in multicast needs to take a performance hit compared to unicast. So if you have a bit of a background in wireless communications, then a wireless system would typically, every client in the wireless system would provide some kind of feedback on its channel quality. That also happens in a Wi-Fi system. And then if you do a unicast transmission to one of the clients, it will pick like the best rate that client can support, and it will adapt to that client. If you now go to a multicast transmission, then you already have to send a packet to multiple users. So you would typically have to pick a rate that is supported by all users. And then, well, if you look at a bigger system, let's go back to the aircraft where you maybe have 200 clients in a single access point, you would have to go in a codec caching system to the rate that is still supported by the weakest client in there. And that could mean the rate you support on the multicast might be 2 or 3 times less than your average rate on a unicast. So what you might face is that you create a gain in or a reduction in network load by coded caching, but then you might lose all of it because the multicast transmission might get a performance hit compared to unicast. So that is really something to keep in mind if you think about codec caching deployments, that unicast system, especially in wireless systems, and that propagates even more if you look into multi-antenna systems where transmissions is highly optimized for a single user, but cannot be optimized for multiple users. So there might be a penalty in switching from unicast to multicast transmission. And obviously, if you want to have a gain by applying codec caching, the codec caching gain must be much, much higher than the penalty you have when switching to multicast. So what does a typical Wi-Fi router do if you send multicast or broadcast packets? It usually doesn't even look at what the clients can support. It typically just selects the lowest rate. Because typically multicast traffic is used like for discovery services. So you want to make sure that every client can receive it. And then even if you put that out, it will use the lowest rate, which is 1 to 6 megabits. And you know there is hundreds of megabits in unicast. So you are using a factor there. And that problem was so annoying to us that we had to actually dig very deep into what Wi-Fi does. And then we had to fix some of those problems with the Wi-Fi multicast. If you're interested in this, we wrote a blog article on what we actually did. You find this on our website on how you can improve Wi-Fi multicast performance. Also, we are facing a very similar challenge when we're exploring avenues to deploy codec caching in cellular networks. So there is, within the standard 3GPP standards, there is this involved multimedia broadcast systems. So the standard supports broadcast or multicast transmissions. But actually, if you look at deployments of 4G networks, very few have this mode activated. I think an Australian operator is one of the biggest deployments. They broadcast sport events, and really, when 5 years back we started the company, there was a lot going on in that cellular broadcast, but then these deployments never really happened. So that's kind of, well, codec caching is kind of blocked for cellular networks with no multicast or broadcast mechanism being available. We still don't give up. So there's a lot happening with 5G. I can tell you about Germany. So in Germany, we also have a terrestrial TV system. That's a system that is called like high towers, high powers. So there's maybe like 100 towers in Germany. They have a cell radius of maybe like 20 or 30 kilometers or even more to provide terrestrial TV. I think they will run another 10 years, but then there is really the idea to replace the terrestrial TV standard with 5G standards and with those broadcast mechanisms. That seems like a long time, 10 years, but the technical standardizations and detailations, they are happening now. So we joined something that is called the 5G Media Initiative. We're very happy to be in that loose consortium. There is big players like Nokia and Telefonica and Rohde and Schwarz, where we're really exploring avenues to make codec caching available in cellular networks. Also something that looks promising to us with 5G is 5G is now frequently deployed in a similar fashion where Wi-Fi is used. It's called 5G campus networks. So universities, larger organizations, they now run their own on-premise 5G networks. And with some partners, we are looking if those could be used to provide TV services in like residential areas or something, and then also use coded caching. So, but that's also something to always keep in mind if you consider deployments of coded caching. You will need that broadcast or multicast mechanism. And then as with the Wi-Fi, a similar thing is happening here. You need to compare yourself to the unicast performance of that wireless networks. Yeah. I think that kind of destroyed the link here. I'm already getting towards the end of my talk. If you want to see codec caching happening, we put a video on our website. So that's typically a demonstration we do when we have visitors or go to trade fairs. We have these 32 Android tablets. This is actually a small mini computer that also has a Wi-Fi network card. And then we play videos on all of them. People can actually touch it, select different videos so they can see it's really live. And then we display some statistics on the network savings. And that's really the computational complexity of the codec caching implementation we run here is really not an issue. So this is like computational power, think something like a Raspberry Pi. So that's sufficient to provide a video service for those tablets. So that's something we're doing here. Also with Professor Kairi at TU Berlin, who is also very active researching codec caching. We're currently building for him a similar test bed for him to run. And then the idea is that he can verify his academic research, the math he did with some measurement results. We're not at a stage yet where we actually publish something on this. This might be happening beginning of next year. So that's something I just wanted to highlight. Yeah. There weren't too many questions. I'm already at the end of the slides I prepared. I hope there might be some follow-on questions we could discuss or discussions. So I'm not sure if we can like open the communication channel to everyone or use the Q&A thing maybe.
Yeah, so the Q&A is already open, and you can ask, type. If they want to speak, in fact, they can raise their hand and we can let them speak. So I had a quick question about this Wi-Fi fixing, whatever you had. So you had something called as aggregation, right?
Yes, so that's actually one of the things we needed to fix in. If you want to go to really high rates in Wi-Fi, there is a aggregation of multiple transmissions. So Wi-Fi transmission really has to fit into time slots. And then in between those time slots, there might be a mechanism to allow others to transmit. And then if you go to high transmissions, you actually would spend a lot of time just not using the airtime. And then you combine multiple packets, that's called aggregation. And then you reduce the waste of airtime by just waiting to fit into those time slots. And that's usually not happening in multicast. So that multicast in between aggregation or not, you can see that this kind of gives us a significant push here. So we really needed to implement that aggregation for the multicast.
Right.
Or to be honest, we didn't have to implement the aggregation. We just had to enable it for the multicast because it's already there and baked into the chips for the unicast. We just had to make sure it's also used for multicast.
Okay. So how many clients? Yeah, please go ahead, Lalitha.
Yeah. So just a quick question on the linear reads. So I mean, is it if the subpacketization is improved, means in the sense if you are able to get lower subpacketization, then that forms a slightly smaller bottleneck as opposed to the subpacketization is very high?
Yes. So if we look at that curve and we consider the centralized scheme, then going along this curve would mean we have to encode more and more users jointly, which would in this Ali-Nielsen scheme mean going to smaller and smaller and smaller subpackets. And then we're typically limited earlier by those practical constraints. So one is the disk I/O read I earlier mentioned, and then if subpackets get as small as like maybe several hundred bytes, then at some point the overhead you need to add. Consider the most important overhead the following: if you sorry, I have to shift some windows here. If you have this joint encoding here that is then broadcasted to the clients, you kind of need to add some overhead telling the clients what parts are encoded here. And then if you go to these really small subpackets, this overhead will just eat up your gain. So there is really a benefit in coded caching schemes that allow for high gains without the need to create really small subpackets.
No, I want to see if it's possible to, formulate the problem in a different way, where the practical constraint is, let's say, placed as a constraint, and then the code design problem is formulated, let's say, right? So when you're asking for linear reads, you kind of maybe say that whenever you want to read, you have to read at least this much chunk, let's say. That is
Yeah.
Can we do code design is my question.
I think you could and you should. To be honest, we're taking a much simpler approach by not formalizing really a problem and solving it. What we can do in practice is like so limited that our solution to that problem is to just generate all the cross product of all the parameters we have, and then for every of those test if it's feasible or not, and then pick the one that performs best. So not a very academic approach we have to this. Certainly worth looking if this can be formulated as a proper constraint in an optimization problem you already have. Also, one could say, well, it's maybe not a hard constraint. Maybe I'm willing. Maybe this is a soft constraint in your optimization problem where you say, well, if I go to smaller subpackets, that might reduce the read rate of my disk, but I might be willing to find the optimal trade-off between small subpackets and read speed and savings on the network. So that, yeah.
Okay, sure, yeah.
Would certainly deserve a more academic approach than what we do.
Okay, thanks.
Andreas, I had another question about this Wi-Fi thing which we are doing. So you said a similar thing would also apply to this multiple antenna scenarios, isn't it?
Yes, so in a multiple antenna system, the clients will provide, or at least what I know about LTE, the base station will send up some training symbols, that's known data. The clients can use those to make an estimate of that matrix channel now with multiple antennas. And then by beamforming or pre-coding, the unicast transmission to this user in particular is highly optimized. It's like directed towards that user. And if now data has to go to two users, that beamforming you would create for these two users is not beneficial for both. So you would kind of have to compromise, or you would even have to drop that gain you usually have by multiple antennas and just use an omnidirectional transmission. So there definitely is a penalty if you need to send data to multiple users, and that penalty will certainly increase if there is more antennas involved.
Right. So the content distribution system, which you talked about in the beginning, yeah. I think you are doing some trials on it. So this is for distribution over Wi-Fi or like cellular?
Oh no, that's really over a operator's network. So that would really be a network in between major cities that like a telco runs. So that's really a wired network then.
Okay. So there the number of clients you're talking about is something of the order of 30 to 100, is it?
Yes.
Okay. So I was just thinking if it is the number of clients are many, and maybe you could. So this aggregation, what you're talking about is like aggregation of clients which have approximately the same channel quality. I guess that's not the case in your specific picture.
It's not the case in my specific picture, but we have done something like on the list of things we would like to do, because if we optimize this broadcast or multicast transmission, then there might certainly be a benefit of grouping those users that have a similar channel gain and then using that channel gain to serve those users. But from an implementation point, that's not very easy to achieve. You would kind of have to include the channel information or rates every user in your system has into your index coding decision.
Right.
Not impossible. We would certainly like to do that. Just haven't found the application or resources yet.
Right.
But yeah, there will certainly be a gain by doing so.
Right. So this is another question which is slightly maybe way out there. So is there some advantage to coded caching in some scenario, let's say some practical scenario in which you don't really have multiple clients?
Coded caching with a single client? No, I don't think there would be any advantage.
Right.
I mean, there is like the trivial advantage that if that one client has something cached, you don't have to transmit that cache again. There is, but no, I think it really needs multiple clients.
Right.
Hi, Andreas. My name is Lakshmi. So a couple of questions to you. So one question is still on this particular slide. So I know that you have got a lot of questions here. Just one more. So when you do this coded caching technique, so you're basically application layer packets. These are the video packets. And then this file is operating at the file layer. So there are some techniques in the literature. Maybe it's not very close to maybe they are difficult from the application perspective. But there are techniques in the literature which do this coding jointly. What they basically do is, instead of XORing the packets at the application layer, you do it at the physical layer. For example, you code words, or you can also do XORing at the modulation level. So the advantage of such a technique would be that, let's say you have two users who have different channel gains, so that they can be served only at different rates. If you XOR at the application, as you said, you have to reduce the rate so that you match the level of the weaker user. Okay, but suppose you this new technique, XORing at the file layer, then you can serve the better user at a higher rate and serve the smaller channel gain at a lower rate, whatever is the bottleneck for him. I was just wondering if you know of such techniques and if you had considered them.
So first thing is, you're right. We are currently only operating at the application layer. I heard about those techniques doing at the physical layer. I remember a paper that was kind of called XOR in the air. It would also like, we did look at the following that might be related. So if we look into wireless channels, we usually also have a error correcting code at the physical layer. So we did try and implement combining the error correcting code at the physical layer with the index code. Found and that might give us some of the gains that you find in those doing the coding at the physical layer. So it might be related. And there's two challenges we faced here. The first thing is that coding became much more complex. But the even more important challenge why we felt we needed to drop that direction is that we couldn't get enough access to Wi-Fi chips to actually build this. So I would assume that this doing the coding at the physical layer is really, really interesting. We would really like to do this, but some of this coding at the physical layer might be baked deeply into the hardware of the chips and not being accessible to us. So I think if we would want to leverage those gains, we would need to figure out how to get access to that deep into the chips. It might even need new chips or maybe some sort of software-defined networking. But yes, I agree that, and we were trying to get some of these advantages. Doing that XOR at the physical layer should give us additional gains, and we would really like to explore that. But really finding it hard to engage with chip manufacturers or people building firmware for them stopped us from exploring this further.
Okay. So basically, if suppose a scheme which essentially does this XORing at the physical layer, but it is transparent to this Wi-Fi module. So you just buy an off-the-shelf Wi-Fi chip, but then you have an algorithm which runs on top, which essentially does this XORing at file layer, then I think something like that would be of great use, right?
I would think so, yes.
Okay. Yes, I have one more question. So when you introduced coded caching, you basically showed that there was just one bottleneck link, right? And then you talked about two applications, the Inflight entertainment system and then the content distribution network. So what are the physical networks that are like, and how close they are to the broadcast network, and how do you match them to coded caching?
I can give you a definite answer for the Inflight entertainment. Here it's just conventional gigabit Ethernet. But in what I would say very strange topologies. So typically they connect those Ethernet cables in like kind of a ring, and then there's like 100 switches in that ring. So it's Ethernet technology, and then multicast that does what it does in Ethernet with switches, like there's IGMP snooping, all these things. So that's just Ethernet with some variations. For the operator CDN network, we're not so sure yet. In the lab, it's 10 gigabit Ethernet, and we're testing with those. But from our partners, where we're looking into this, we know that they have other kinds of multicast networks, but they haven't shared with us yet what exactly those technologies are, and I'm not really an expert. So from where we ran tests in the lab, it was still, again, Ethernet.
Okay, so in your product applications, you simply use an off-the-shelf multicast protocol. Is that correct?
Yes. So that's we're switching to UDP then, because in multicast there's no like session maintaining, and then if the switches support it, then we would send that UDP packet to that Ethernet switch only once, and then it would replicate it on the outgoing ports. And then in the applications we are looking in, the bottleneck is really from the server to the first switch. And then that switch does this packet replication kind of cost-free. So the good enough switches have that baked into their hardware packet replication somehow. Yeah.
Okay.
But
thank you, Andreas. Thank you so much.
Really, a wireless network feels to me much more suitable to the whole coded caching idea, because, well, let's leave aside the multiple antenna systems for a while. That omnidirectional antenna really feels like the multicast is for free. You would send a packet into the air, and it's like multicast by definition. It's just a matter of the clients listening to it.
Yeah. Thank you, Andreas.
I think with that physical layer coding idea, if that's a paper you wrote or in preparation is or something you can share, and you want some feedback if that matches to what we do or not, and you're willing to send this, send me an email, and I can give you a more detailed opinion if that's interesting to you.
Yeah, sure. So this basically comes from I think this entire literature follows from the paper you mentioned, exhaust in the air, and I think there have been more and more sophisticated techniques, mostly from theoretical side, showing that you can achieve the capacity upper bound. Yeah, so I will maybe forward one or two references to you.
Yeah, that would be super nice.
Thank you.
So I had one more question. There is a previous speaker, Professor Petros Elia, who talked about this privacy issue in the context of clients not knowing about the demanded files of other clients. Right. So the idea is like it's called demand privacy in the academic literature. I should not be figuring out what this other guy is demanding. Have such concerns in the applications that you are looking at all? Like, does that make sense?
Yeah, I guess it does make sense. We don't have it in there. As this is jointly encoded, we would forward along. So I think in our scheme, a client would not know which client is requesting which file, but it would know what files are requested in total just by listening to it. So no, our implementation cannot provide this.
Okay.
I think also, and I have to admit, this is the first time I'm hearing about this demand privacy. I know that Petros did a lot about looking to this in the context of encryption, but I have to admit that this demand privacy is new to me, so I would have to take a look at this.
So there has been some recent interest, maybe in the last 1 year, 1.5 years, this topic, like quite a few papers which are adapting the traditional schemes to the demand private scenario have come out from various places.
So just from the commercial point of view, we never had a customer asking for this. So.
Right. Okay, so if there are any other questions, please raise your hand or use the phone, use the mic. Okay, then we can thank the speaker. So thank you so much, Andreas, for being here and giving us this talk. I think most of us are basically academics, and we really enjoyed looking at taking a different look at this whole implementation side. So thanks a lot, and hope to see you sometime.
Yeah, so thanks a lot for tuning in, and yeah, I think you see my contact details. If you want to reach out, do so, and then enjoy the rest of your day and the rest of your conference. Thank you very much.
Yeah. So for the attendees, the next talk is going to be on Monday at the same time.